PCH students, here we are with 13.2, recursive definitions. And the objective is to use sequences to find recursively solve problems. So a recursive idea is you refer back to a previous term. So in this first example, we have t sub 1 equals 3. That's the first term is 3. And t sub n equals 2, t sub n minus 1 plus 1. Now notice the recursion here. N minus 1 and n. This is the nth term, and t sub n minus 1 is the term before it. So you take twice the term before it and add 1. So in this first example of t sub 2, it would be twice t sub 2 minus 1 plus 2, or twice t sub 1 plus 2. So that's twice 3 plus 2 equals 6 and 2 is 8. And so t sub 3 would be twice t sub 2 plus 2, twice 8 plus 2, and we get 16 and 2 is 18. And t sub 4, twice t sub 3 plus 2, so that's twice t sub 3, which is 18, plus 2, 36 and 2 is 38. I think that's right. Twice t sub 6 and 2 is 8, and then 16, yeah. Now, let's look at another sequence and come up with its recursive formula. So remember, for a recursive formula, you have to specify two things. You have to say what the first term is, 23, and then you have to say that the nth term is the previous term, in this case, minus 3. We have a common difference here of negative 3. It's arithmetic. You keep dropping by 3. Well, remember we had an explicit formula for arithmetic. T sub n equals t sub 1 plus n minus 1 times d. And so t sub n is 3 plus n minus 1, 23 plus n minus 1 times negative 3. And so t sub n is 23 minus 3, 26 minus 3n. Notice how these formulas look very different. Because one is defined explicitly. You get the nth term in terms of n. And a recursive formula, you get the nth term in terms of the previous term. And so that's not enough. The recursion alone is not enough. You also have to be given the initial condition. Now let's find the first 5 terms of this sequence and find an explicit formula for t sub n in terms of n. So the first term is 64. And now by this formula, we're going to take half the previous term. So the second term will be half the first term. So half of 64 is 32. And t sub 3 then will be half of t sub 2. So that's half of 32, 16, and then 8, and then 4, and so forth. And I think you can see we have a geometric sequence here. So t sub n equals t sub 1 times r to the n minus 1. And so explicitly we have, I believe our first term was 64. Our common ratio is a half to the n minus 1. This is fine. You could write it as 64 times a half to the n times a half to the negative 1, and then write it as 128 times a half to the n. So I'd accept that too. Okay? Now, be careful though. A lot of kids are tempted to call this 64 to the n. Oh no. No, we are not going to do that. No. Because exponents come before multiplication. So even though this is tempting to take 128 times a half, you can't do it. Can't do it. Okay? Now, the population of a certain country grows as a result of two conditions. The annual population growth is 1% of those already in the country. This growth rate equals the birth rate minus the death rate. But also we have 20,000 people immigrating into the country each year. So the population is now 5 million people. What will the population be in 20 years? So we can come up with a recursive definition. P sub n equals the growth rate applied plus the immigrants. So P sub n equals 1% more than we had already. So it'll be the original population plus, from the previous year, plus 1% of that population from the previous year. So that's P sub n minus 1. That's the growth rate applied. And the immigrants will just always be a fixed 20,000 added on every year. Now there's an easier way to write this, and that's to say 1 plus 0.01, or 1.01 times P sub n minus 1 plus 20,000. Now, is this going to be arithmetic or geometric? Because the adding the 20,000 would be arithmetic. Multiplying by 1.01 each year would be geometric. But I put these two together, we're going to find that we don't have either. So I can't use a quick formula for that. What we can do is use the calculator to quickly come up with this. Take your 5 million, hit enter, and then hit answer 1. Actually, it'll do this automatically if you hit times, because times is a binary operation. And if you just hit times after enter, it assumes you want to multiply the previous entry. Times 1.01 plus 20,000, enter. Now do that 19 more times, and you'll get your 6,541,330. We don't have an explicit formula for this one. We could develop it, but for right now, this is an example of recursion that doesn't relate to either a geometric or an arithmetic sequence. Now we can also take a spreadsheet approach, and I want to show you how you can use spreadsheets to quickly come up with these ideas. So let me take a pause while I get out the spreadsheet. Okay, so here we are in a whole spreadsheet, and all I've entered so far is the year and the population. And our year 0, we had a population of 5 million. So we want to put year 1 here. I want to show you a little trick here with spreadsheets. I'm going to use an equation, equals, and I want to just click on the previous cell above it, and then add 1 to it, and then hit enter. And so it made 1 there. But notice it's showing up 1 here in the display, but up here in the FX it shows you the formula. And that is it's taking a sub 2 plus 1. Now, when I copy this down and do Control D, I should do it one more time. There, it's not only copied down these numbers, but see how the formulas have changed? That's called relative referencing. So even though this one said A2 plus 1, when I copied it down, it assumed I want to do the one above it. So that's why it's A3 plus 1 here, to get the section for A4. That's going to be handy now when we do our recursive formula. We can say for our next year's population, it's going to equal the previous year's population, so that's cell B2, times 1.01. There's the 1% increase, 1.01. And then add on the fixed immigrants, 20,000 immigrants. And there. So there's our increase plus the immigrants. And now we can Control D this all the way down. Control D to copy down. And there's our 6,541,330.28 for our population after 20 years. Okay, so that's the spreadsheet approach. Now let's look at another kind of recursive sequence where you recur to 2 previous terms. And the Fibonacci sequence is the classic example of this. So in the Fibonacci sequence, we get T sub 3. We have to actually have an initial condition of 2 of the terms because it says any term is the sum of the previous 2 terms. So T sub 3 equals T sub 2 plus T sub 1. So that's 1 and 1, which equals 2. And T sub 4 is T sub 3 plus T sub 2. And so that's 1, T sub 3 is 2 and 1, and you get 3. And it looks arithmetic for now, but no, T sub 5 is T sub 4 plus T sub 3. So that's 3 and 2 equals 5. And then 3 and 5 will make 8, and then 5 and 8 will make 13, and so forth. And that's your Fibonacci sequence. Now you can do this on your 89 quickly with hitting 1, enter, and then just hit the plus, and it'll say answer 1. And for answer 2, you're going to have to use that stuff at the bottom of your screen there to come up with the answer. Answer is on your screen above the opposite symbol, the blue ANS, and you have to put 2. So what this is doing is saying add the previous term, the most recent display, and the display just before that. And then you can keep hitting enter to generate this sequence. So let's take a spreadsheet approach on this and see how it works out. Right here I'm back in Excel again, and I've made my first 2 terms are 1 and 1. And here's the index of the term. And let's do a few terms there. I just want to come up with the formula equals like we did before, the previous term plus 1. This is actually called the identity sequence. Let's have that go down a ways. Now the Fibonacci sequence over here is the sum of the previous 2 terms. So we put in equals that term plus, and then click on the cell, that term, and hit enter. And then copy that down. And we get a bunch of numbers in the Fibonacci sequence. What I want to point out to you, though, is this arithmetic or geometric? Well, clearly it's not arithmetic because you're adding nothing here, adding 1, adding 2, adding 1, adding 2, adding 3, adding 5, and so forth. So it doesn't have a common difference. And does it have a common ratio? Let's look at the ratios and look at the ratio of any one term divided by its previous term. Oopsie, I did that wrong. This should equal this term divided by the previous term. There we go. Now let's copy that down. Control D. And as you see, no, it's not a common ratio, but it's approaching a common ratio. And one of the amazing things with this is I could change the first two terms to like 12 and 20. And I'd get a different set of Fibonacci numbers. But notice how this ratio of the terms keeps approaching the same thing, this mysterious number 1.618033989 and so forth. And I hope we can get a few more digits on this. Here, let's set this up to data. No, it's under, hold on. Let's go back to the home screen again. It's under formatting the cells. Format the cells to hold numbers, general, sample, huge number of decimal places here. Okay, as many as we can. Okay, boom. And so now we got to stretch this out a little bit. There. And then we can get a few more digits. See, that's still changing as we get down here, but it is getting closer and closer to something. And this thing is called the golden mean. Even if I change these terms back to 1 and 1. Yeah, some of the initial values are different, but then it still approaches this 1.6180339, sometimes abbreviated by the symbol phi. Okay, back to the other board now. Now there actually is an explicit formula for the Fibonacci sequence. Would you like to see it? Okay, you asked. It's huge. Not exactly our standard form for the arithmetic or the geometric. But it has a number in here, this 1 plus the square root of 5 over 2, which calculates out to be 1.6180. And there it is, the Login Amen. Oh, I think you know what that means. Try and unscramble that for class. Login Amen. It shows up over here. This 1.6180339885. We get close to it. Okay. Oh, and check this out sometime. Try taking this formula and putting in 24. See if you get 46,368. All right. Flange out.